morning. Today we will start with some darker side of cryptography, which is about hardness and advance. So the first talk will be by she will talk about a refined hardness estimation of that problem.
Thank you. And I introduce myself. My name is Wen. I'm the reporter of this mission, and our work named a refined hardness estimation of LWE in two-step mode. Okay, here is the constants of our work. The first is the introduction of LWE estimator, and the second one is our contribution. The third one to the sixth one is the detail of our contribution. So now is the first part. Before we introduce the LWE estimators, we parse them into two types, the PKC only mode and the two-step mode. The PKC that we only do the reduction. Sorry, wait. The microphone is not working. And the PKC only mode is we just do the call the PKC only and get the target vector of the LWE of the LWE problem, because LWE can be reduced to the USVP. Yes, and for the two-step mode, we not just do the PKC process, but we do the search process such as the sieving or the enumeration at last. Yes. So here are two different estimation in this screen. And the left one is a two-step mode, and the right one is the PKC only mode. The first two-step mode estimation is the BDD estimator, and the famous PKC only mode we know is the core SVP. Yes. So our work is based on the two-step mode, and we have proposed two estimators for LWEs. One is the refined LWE estimator in two-step mode. It combines the PNG-PKZ sieving and the distribution of the target node. And we also give a lower bound estimation of LWE, which combines the PKZ and the sieving and the GSA and the expected norm. Yes. Here is the comparison among the different LWE estimators. The last two is our work. Okay. Now it is our contribution. Our first contribution is we prove in theory that the two-step mode is faster than the PKC only mode in solving USVP on the so okay. Oh. Try to talk a little louder. Okay. And under the GSA, and the second contribution is we construct a refined LW hardness estimator in two-step mode and give two experiments. One is we verify the accuracy of the success probability used in refined LW hardness estimator, and the other we give the verification experiments for efficiency of two-step mode by refined LWE hardness estimator. Yes, and the third one is we give a lower bound estimation for LWE in two-step mode. The fourth one is we will evaluate the security bit of these PQC schemes, both by the refined LWE hardness estimator and the lower bound estimation. Now, we introduce our first work, the efficiency of two-step mode. We prove under the GSA assumption, and the heuristic one is with our based also our basic heuristic assumption is the Gauss heuristic assumption, and the heuristic 2 is the GSA. And the heuristic 4 in 7 means that if the lattice basis has the same quality with PKC beta reduced basis, then the basis cannot be further improved by PNG PKC beta J or the PKC tool. So we give the theorem 1 here. We assume the Gaussian heuristic and GSA and the heuristic 4 in the reference 7 hold. Then we can prove that there exists a parameter choice for the two-step mode, which solves the USBP's instance in less time than the BKC only mode. And our second work is we defined a refined LW estimator in two-step mode. And before we design it, we should consider about the following two questions. The first one is how to estimate the success probability of finding the target vector. And the second one is how to estimate the time cost and the memory cost. So for the first question, we just propose the success probability computation model combining BKC and sieve. And for the second question, we just compute the expected time cost and memory cost through the success probability. Okay, now it is the notation of our of the probability station. And the W is the event of the solving LWE successfully during running progressive BKZ or the final high dimension progressive sieve of two-step mode. And the W beta 1 means the event of solving LWE by BKZ beta successfully. And the E beta I1 is the event of solving LWE successfully during the process of running progressive BKZ from maybe BKZ beta 1 to BKZ beta I. And the WDSVP2 is the event of solving LWE by DSVP dimensional progressive sieve successfully. And the EDSVP2 is the event of finding the projected projection of the target vector exactly after a DSVP dimensional sieve during the progressive sieve. It's different from the WDSVP2. So based on the heuristic 3 and the heuristic 4, we give the cumulative probability of solving LWE in our refined LW estimator in two-step mode. The heuristic 3 said that the success event of each BKZ is independently, which is similar with the leaky LW estimator. And the heuristic 4 means that the success event of each sieve in progressive sieve is dependently. It says that the maybe WI2 contains the WI minus 1, 2 success event. Yes. So based on these two heuristics, we have the PRW. It's the cumulative probability of solving the LWE. And the first probability is PRE beta and 1. It means we successfully solve the LW problem in progressive BKZ. And the 1 minus PRE beta and 1 is the failure success, is the failure probability of solving LWE in progressive BKZ. And we just dot the PRWDSVP2. It means we solve it in the dimensional DSV dimensional the DSVP dimensional sieve at last. Yes. So if the PRW is equal to 1, it implies that all the LW existence with the specific average value and variance could be solved. And it is time to terminate our estimator. So we also give a verification experiment of this work about the equation for the PRW. The left picture shows that the prediction of the success rate of solving LWE given by the equation 4 is consistently with the experimental result. And we also give the computation method for the gate count and the memory count. Firstly, we should consider the cost of BKZ like this one, and the second one is BKZ cost plus the sieve cost. And so we just multiply them to their corresponding success probability and summarize them all in total and got the G. And we can get the B in the similar way. Yes. Okay. Now this picture shows that the two-step mode is faster than that of using BKC reduction only. Here, the blue dashed line is the BKC only estimation, and the red one is the two-step mode estimation, the lower bound of the two-step mode estimation. Yes. Okay, now it's the improved conservative estimation for LWE. Is our third work. Before that, we also want to introduce the notation. The mainly one is a new, the RHF delta beta. It means a new root emit vector of lattice basis after one BKZ beta tour on the GSV, which is different from the delta beta. And the MD delta M means the minimum dimension for sieving to find the target vector with norm M. And we can see that we should give the conservative estimation for LW based on heuristic 5 and heuristic 6. The heuristic 5 is BKZ is the optimal algorithm for lattice reduction, and the heuristic 6 is the best way of solving USVP gamma or LWE by performing the lattice sieving on a projected lattice of a reduced lattice basis satisfying the GSA. So if these two heuristics hold, then our conservative estimation can be proved that it is strictly lower than the hardness of the LWE. Okay, now we introduce about how to compute the RHF delta beta. Firstly, we should give the basis quality delta and the lattice volume V. Then we can compute the Gram-Schmidt length under GSA. And if we have the Gram-Schmidt length, then if the delta is larger than delta beta, then we should firstly compute the beta 0 after our BKZ beta by Gaussian heuristic. And then we can expand the remaining GS length by the GSA. After that, we can get the new RHF, the RHF delta beta. Yes. And if the delta is smaller or equal to the delta beta, it means that the lattice basis cannot be further reduced by BKZ beta. So here we just let the RHF delta beta becomes delta. Yes. Okay. So here is the lower bound estimation of our work. We can see that if we can find a beta and DSVP such that the one more BKZ beta prime before the last sieve cannot shorten the total cost for solving LWE, then we can find the lower bound of the LWE. Yes, and just to denote the cost of the sieving at the DSVP dimension to be the cost of our lower bound estimation. And the theorem 2 ensures that our lower bound estimation is strictly lower than the actual cost for solving the USVP gamma in almost all lattices. Also, we have optimized the number of LWE samples to minimize the lower bound security estimation by algorithm 5. And the last is our estimated result. We can see that the estimation of the NIST standards by our refined LW estimator drops by 2.2 to 4.6 bits. in the time cost, in the gate count, yes. And we also estimate it using our conservative LW estimation. Our lower bound estimation is 4.17 to 8.11 bits higher than the core SVP estimation. And if we consider the dimension for free technique, the lower bound may be decreased by 3.42 to 14.76 bits. So it declares that the core SVP model is not conservative enough to offset the influence of the dimension for free. Yes. And thank you for listening my report. Yes.
Okay. Thanks for your talk. Do you have any questions from the audience?
So can you tell me again what you're doing in the intermediate step? So you're doing a PKZ reduction, then you do something that is new, and then you do more PKZ reduction.
I do some PKC reduction.
So PKZ does repeated lattice reductions.
Oh,
then
yes.
Some reductions, then you do some intermediate step, which is the new thing, and then you. What is the two step?
The two step.
What is in the middle?
Two step is we just firstly call maybe some rounds of PKZ. Then we call a sieve algorithm or the enumeration algorithm to find the target vector. We just use the reduction process to increase the latest spaces quality, not to find the target vector at last. Yes.
You do that on the complete basis or on the block size, on the PKZ block size?
Oh, we have a terminal condition. Yes, we have the estimation. Okay, so this picture. You can see that we just do the because maybe we have a block size strategy, like a trivial strategy or some optimized strategy. Then if we input the strategy, then we just iterate them, and if the and we will output the minimal cost of the two-step mode in two-step mode. The BKZ maybe BKZ will terminate before the cumulative probability becomes 1. Here the p total may be smaller than 1, and then we will do the DSVP as a sieve algorithm to increase its success probability. And then if the total successful probability becomes 1, then we can get one of the cost. And we will compare all the such cost in total to find the minimized cost. Can I? Okay, thank you.
Thank the speaker again for your brilliant talk.
这样也可以吧，没问题，因为它不是完全的全屏。下一下来吧。这怎么去除？再见，等一下。
It's not. So our next speaker is Johan Lee, and he will be talking about cryptanalysis of the hieroglyph lattice.
Thank you for your introduction. The title of my talk is Cryptanalysis of Pilgrim lattice-based signature scheme. This is the joint work with Moito Suzuki, Siduo Zhang, Thomas Espito, Yang Yu, Mehdi Tiboti, Meshuiki A, and I'm Xiuhan Li. I'm from Shandong University. This is the cryptanalysis work of Penguin lattice-based signature scheme. And our target is Penguin, which is the first round of Korea post-quantum cryptography competition candidate in 2023. And in this work, we use two kinds of techniques, parallel pipe learning and lattice decoding. We first use the parallel pipe learning technique to find the approximate the signing key, and then use the lattice decoding to correct errors from the approximations. In these attacks, the signature samples required for the attacks is around 25,000 for the reference implementation and 11 million for the specification version. Let's start from some background knowledge. A lattice is a discrete subgroup of the set of real numbers, and it's the set of all integer combinations of linearly independent vectors, and the matrix B is the basis like this. And the lattice has infinitely many bases, and the B, in the figure, in the B is the good basis, and the G is the bad basis. And then the good basis is respecting short and orthogonal, which can be used to solve the approximate closed vector problem. And the bad basis consists of much larger vectors, which is a little help to find the closed vector. And each basis defines a parallel pipe like this. And for the target vector T, good basis has a good approximation factor compared with the case of with the good bad basis. For Barber's round of algorithm, outputs the lattice point V such that V minus the target vector T is in a parallel pipe. And the lattice in lattice-based signature scheme, hash and sign construction is very important. So the signing is to solve the approximate vector closed vector problem. And in the early stage, GGH and N2 sign, GGH and N2 sign use deterministic round of algorithm to solve the CVP. And signature minus the hash message is always in a parallel pipe. The distribution of signatures leaks the information of secret key, so they can be broken by some famous parallel pipe learning attacks of Ren and Regev. So those early construction like GGH and N2 are insecure. So in the GPW, the authors presented a provably secure framework, which replaces deterministic round-off algorithm with chapter sampler. They run the hashes with random Gaussian sampling on lattice, and the distribution of signatures follows some Gaussian, and is dependent of the secret. And the Falcon signature scheme has been selected by LIST for standardization in 2022, and it's an efficient initiation with GPW framework with over N2 lattices. So it has small size of public key and signature, and it also has good performance. But due to the signing requires Gaussian sampling and floating point operations, it's also complicated. And for the Gaussian sampling, it suffers from the side channel attack. So designing a simpler and comparably efficient variant of Falcon is a tempting choice. So the Penguin signature is proposed. Penguin signature scheme is one of the candidates in the first round of the Korea post-quantum cryptography competition, and it proposed as the high-speed version of Falcon. So it avoids a Gaussian sampling and adapt a new sampler based on the centered binomial distribution. So it's simpler and along with comparable efficiency, and it's too easy to mask to prevent the side channel attack. However, Penguin does not offer a proof of security, so it's natural to analyze it. And let's give more details about the signing. It first used the bar-based round-off to find the cost vector and then plus a binomial vector instead of using Gaussian sampling. You can this the algorithm signing. And we have the practical distribution. The signature is equal to B times minus R1 minus J1 R2 minus J2, and where the coefficients R1 R2 are uniformly distributed over minus 1/2. So the distribution of signature is a hidden linear transformation of a lower distribution, and then therefore we can perform practical key recovery attacks against the peregrine by learning the hidden linear transformation. So more visually, the peregrine signatures are always in adjacent parallelepipes seen the figure on the left, rather than a short parallelepipes seen the figure on the right. So penguin are also insecure. So the distribution of signatures wouldn't leak the information of secret key, and we can learn the hidden transformation by learning parallelepiped learning of rain and regev. So in this work, we focus on the parameter set of Penguin 512, and to be surprised, there are some differences between the reference implementation and the official specification version of Penguin. And for key generation, in specification, the coefficients of secret polynomial are drawn from centered binomial distribution, and it checks if the Gram-Smith norms of B are less than the bound. And in the reference implementation, this check is commented out. So which yes, the risk of weak key. And for the signing, the specification uses the binomial parameter mu1 and mu2 are both equal to 26, and the reference implementation in fact use the mu1 is equal to 6 and mu2 is equal to 0. So we can mount practical attacks against the two versions of Penguin, and much more smaller binomial parameter selections can facilitate our attacks. And in the key part of our attack is how to learn a hidden transformation. Before introducing that, we revisit the parallelepiped learning of rain and regev. So we first they first give the hidden parallelepiped problem. So in order to solve the hidden parallel pipe problem, they first use the covariance leakage and then to approximate the grand matrix, then compute the factor L where the matrix B can be defaulted into C by multiplying L matrix L, and the local minima, the CI can be solved by gradient descent. So the approximation of BI can be founded by multiplying the inverse matrix L. So the when and the Regev parallel pipe learning attack can be extended to more general hidden transformation problem in our case. So for this problem, the distribution is the for Penguin is the uniform distribution minus 1/2 plus some center binomial distribution B mu one or B mu two. So our key recovery algorithm can be divided into two steps. The first step is distribution deformation, and then the second step is gradient descent. So we also have used the covariance leakage to compute the matrix L, and the matrix B can be defaulted the matrix C by using the matrix L such that the covariance DC is equal to identity matrix, and when the covariance D is also identity matrix when the C is orthogonal. So distribution deformation reduces the hidden transformation problem instance regarding DB to the one regarding DC, that such that the covariance DC and D are both equal to identity matrices. So in this fork, we also focus on the fourth moment, and so we can have the following expressions of the fourth moment and its gradient. So at lemma one shows the local minima of the fourth moment function can be obtained at CI, and there are no other local minima. So therefore, local minima CI can be solved by gradient descent. So in the case of Wen and Regev attacks, they have the fourth moment function and its gradient. So in our case, in the case of Penguin, for different binomial parameter, we have the following expressions for the fourth moment function and its gradient for specification and the reference implementation version. So by adding the binomial parameter, this countermeasure can cost our attack. Next, we give the practical key recovery attacks. We have used the parallel pipe learning attack to find the approximate key, and then we used the lattice decoding to correct errors. So the B, we assume that B is the secret key, and then the B prime is the approximation of B. So we use the Thomas Prest decoding technique to correct errors. For his attack, at least half of the coefficients of E is equal to B prime minus B are in minus epsilon. So the difference D is equal to rounded B prime minus B has zeros in at least n-half coefficients. And for untrue equation, B times H, when the public key H is equal to 0 mod Q, then the rounded B prime times H is equal to the difference D times the public key H mod Q. So the secret key can be fully recovered by linear method. So our probability-based guessing strategy is slightly different from the trick of Thomas Prest. We don't exploit a threshold epsilon and select n-half coefficients which are correctly rounded with the highest probability. In lemma 2, we actually select the n-halves, the smallest fractional part of a B prime, and the standard deviation is inversely proportional to required signatures, and constant C sigma can be derived by calculating. And so for each the experimental results validate the effectiveness of our attacks, and For each instance and each sample size, we randomly chose 5 starting points to perform the gradient and count the number of successful secret key recovery attacks. And for reference implementation, around 25,000 signatures are enough to perform the successful key recovery attacks with good probability in half an hour. And for the specification version, by using around 11 million signatures, the security can be fully recovered in 20 hours. So in conclusion, we present practical key recovery attacks against Penguin. We can practically break 2 versions of Penguin 512 by using a relatively small number of signatures and in few hours. So the assembly can be extended to the case of the version and the high dimensional version of Penguin. So more efficient countermeasures against statistical attacks need further investigation. That's all. Thank you very much.
So we have some audience. Anyone has any questions? Yeah, this one. Can you go back to the previous slide? Go back to the previous slide. Do you have any thoughts on the preventions against your attack that they can maybe use?
Our experimental results shows that the larger binomial parameter can increase our cost of our attacks, right? So, but in the paragraph, they set in the specification says that the mu1 and mu2 are equal to 26. But if we increase the binomial parameter, the efficiency don't guarantee maybe. So we could select different distribution, like uniform distribution like this. So it's not easy to fix the Penguin.
It seems like it's hard to fix it while keeping its efficiency, I guess. Okay, any other questions from the audience? On the next speaker, let's take the students. And she will talk about algebraic embedding for unstructured analysis.
Thank you very much. Hi, I'm Madalina, and today I'm going to talk about this joint work with Zvika Prakirsky and Devika Sharma called on algebraic embedding for structured lattices. The outline of my talk is the following. First, I will briefly recall what learning with some of its algebraic variants and their state of the art. Then I will show you our contributions, which include improving the order LWE hardness result and a gradient of hardness from ring LWE to LWE. But first things first, let's see what lattices are and why they are helpful. A lattice is just an infinite set of points with periodic structure generated by some linearly independent real vectors with integer coefficients. One important hard lattice problem is called approximate shortest vector problem, which says the following. Given a lattice, find a non-zero short vector up to some approximation factor gamma. For a polynomial approximation factor, as far as we know, this problem seems to be resistant to quantum attacks, so it might be a good candidate for designing post-quantum crypto schemes. Nowadays, it's not this problem that is directly used as a basis for designing post-quantum crypto schemes, but some intermediary computational problems. One of them is called learning with errors. This problem is defined by an integer modulus q and an error distribution psi, which produces with high probability short elements in ZQ. The LWE distribution is defined as follows. We have a secret vector S with entries mod Q and of dimension n, and it produces outputs of the following form. We sample a vector A over the same space ZQ to n as the secret. Then we take its inner product by the secret S, we divide by Q, and then we add an error E drawn from the distribution psi. The LWE problem has the variant called search and decision. The search variant asks you, given some LWE samples, to find the secret, whereas the decision variant asks you to distinguish between the LWE samples and the uniform ones. The LWE problem has reductions from hard lattice problems, so we can think of using this problem as a basis for secure post-quantum crypto primitives. This problem has proven to be a versatile one as it's designed, as it enables designing many advanced crypto primitives such as homomorphic encryption schemes or identity-based encryption schemes. One main drawback of these schemes is their high computational complexity due to several matrix by vector multiplications, so they turn out to be not very efficient. One way to increase their practical efficiency is to add an algebraic structure in the LWE problem. For example, we can think of replacing the matrix by vector multiplication by polynomial multiplications or multiplications between ring elements. With this idea in mind, many algebraic variants of LWE have been proposed in the last years. But for this talk, I will only recall about the ring LWE problem and the generalization of it, the order LWE problem. These problems deal with algebraic number objects. So let's set up their stage first. They work with what we call number fields, defined as Q of x mod f for irreducible polynomials f with integer coefficients. As the LWE problem, they are also defined by an integer modulus q and an error distribution psi, which produces short elements with high probability in the number field this time, not in ZQ. Introducing the ring LWE problem, let's see another important algebraic object called the ring of integers. You can think of this ring as the polynomial ring Z of x mod f for a cyclotomic polynomial f. LWE distribution is defined as follows. We have a secret element S from what we call the dual of the ring of integers, OK dual Q. And we create samples in the following way. We sample elements A uniformly over OK mod Q. We multiply A by S, divide by Q, and then add an error E drawn from the distribution psi. all the computation is made modulo OK dual. Now, in order to see what order LWE problem is, as its name suggests, we should see first what an order is. By an order, I mean a subring of the ring of integers OK of finite index. You can think of instance as g of x mod f or the ring of integers itself. The order LWE problem can be obtained from replacing the ring of integers in the ring LWE1, okay, by general order O. So the order LWE problem is a generalization of the ring LWE problem. As the LWE problem, the search and decision variants of these problems can be defined as before. From now on, I will refer to the problem as either RLWE or OKLWE, and to the LWE problem as OLWE. The ring LWE and order LWE problems are interesting ones, as their hardness relies on solving lattice problems on lattices in number fields. More precisely, it was proven that solving decision ring LWE problem is at least as hard as solving a process VP on all ideals of the ring of integers. And later, this was generalized into showing that solving decision order LWE is at least as hard as solving a process VP, but on a subset of ideals of the order involved. Moreover, these two problems are related by an error-preserving reduction from RLWE to OLWE in both variants. And further, there was also shown a reduction from OLWE to LWE, also in both variants. In this work, we show that we can solve, if we can solve the decision order LWE problem, then we can solve a prox SVP on all the ideals of the order if we assume a complementary condition on the modulus. Moreover, from OLWE to RLWE in both variants, we get as a consequence an extended Hardness result of ring LWE to involve lattice problems on ideals on the order. Moreover, we show that there are some special orders in number fields we call alpha drowning, for which their corresponding order LWE problems are equivalent with the unstructured LWE problem. So for these special orders, their corresponding order LWE problem loses algebraic structure and cannot be then used for building efficient cryptoprimitives. So now let's go into our first contribution, improving the order LWE hardness result. To get such a hardness proof, we simply follow the PRSD BBPS hardness blueprint, whose main ingredient is a conversion of PDD samples into order LWE samples. This conversion uses discrete Gaussian samples drawn over an ideal I of the order O. The PDD samples are defined using the dual of the ideal. In order to convert the PDD samples into order LWE samples, we have to cancel the ideal I by finding compatible isomorphic maps F and G. These maps do the following. The map F sends the discrete Gaussian Z from I mod Q to the A part of the LWE sample from O mod Q, and the inverse of G sends the PDD secret X from I dual mod Q to the OLWE secret S from O dual mod Q. These maps have been studied in previous work, and there is a result called cancellation lemma that shows a construction for such maps for general orders, but considers only a subset of ideals of the order involved.
In this work, we show that such maps can be constructed by considering all the ideals of the order under a complementarity condition on the modulus Q. The idea we use for this construction is the following. We embed the given ideal I in a very carefully chosen ideal P in such a way that we get an isomorphism from P mod Q to O mod Q by applying the previous cancellation lemma, and to also get an isomorphism from I mod Q to P mod Q by applying a previous result due to the embedding of I in P. Having these two intermediary maps, we therefore can compose them to get our desired map F, and by dualizing the maps, we can also get the map G. The way we find this good ideal P is by using Jordan-Hölder filtration, which is an algebraic technique of ideals factorizations in number fields. To the best of our knowledge, this technique was not used in prior work in this context, and we believe that this extended cancellation lemma might be of independent interest. In order to get an extended result of the Ringel-WE problem, we simply need to focus on our to Ringel-WE, as then we can compose this reduction by our previously shown Hardness result of OLWE. The way we get this reduction is made similarly as in previous works by using an element T from what we call the conductor ideal of the order. This element T sends the ring of integers OK to the order O, or secret space of OLWE, O dual mod Q, to the secret space of Ringel-WE, OK dual mod Q. Given an input AB, we simply multiply the second coordinate by this T. We therefore get a penalty error by this factor T in the resulting error distribution in the Ringel-WE problem. So ideally, we would want this T to be short. The existence of such a short multiplier is assured by previous works. And now let's get into our second contribution, gradient of hardness from Ringel-WE to MWE. Here we work with a number field K and an LWE modulus Q. We also have an integer modulus P co-prime with this modulus Q. And assume we know the integer, the prime factorization of the ideal generated by this P. Using the prime ideals, we can construct a chain of orders starting from the ring of integers OK and ending with Z plus P OK. By repeated applications of the previous result, we therefore get a chain of error-preserving reductions starting from the OK-LWE problem, which I recall you, it is the commonly used Ringel-WE problem, and ending with the order LWE problem corresponding to the order Z plus P OK. The reductions hold in both variants. We also have a reduction from the last order LWE problem to the unstructured LWE problem with a penalty error. We show in this work that if this order Z plus P OK is what we call alpha drumming by a good choice of the parameter P, then the last problem becomes equivalent with the unstructured LWE problem. So in this sense, we get a gradient of hardness results. Showing this work that for if Z plus P OK is what we call alpha drumming for a good choice of the parameter P, then the last order LWE problem becomes equivalent with LWE problem. So in this sense, we get a gradient of hardness from Ringel-WE to order LWE to LWE. This chain of reductions also offers intermediary order LWE problems, which are potentially harder than the Ringel-WE problem and might be useful in building efficient crypto primitives. Now I know that I mentioned about alpha drowning orders, so let's see what they are exactly. They deal with the behavior of Gaussian errors of parameter alpha when taken modulo the dual of the order. This behavior can be equivalently analyzed by taking the coefficients of the error with respect to the z basis of the dual of the order and taken mod z. We say that an order is alpha drowning if the last n-1 coefficients conditioned on the first coefficient are nearly uniform when taken mod z to n-1. Example, in the case of a power of two cyclotomic field, the previous order z plus p of k is indeed alpha drowning if p is taken much bigger than 1 upon alpha. So these specialized orders give us the idea of showing a reduction from LWE to order LWE for both variants. Namely, given an input AB0, we embed the coefficients of the vector A with respect to z base of the order O to get the first coordinate of the output. Then we embed the coordinate B0 with respect to the dual z basis of the dual of O as the first coefficient, and we sample the other coefficients uniformly over R mod z. Get a second coordinate of the output. We show that if the input is LWE, then the output is nearly order LWE by using properties of alpha drowning orders. To sum up, we have shown extended hardness results of order LWE and ring LWE problems to consider lattice problems on all ideals on the order. We have also shown equivalence between order LWE and LWE for special orders in number fields. Some follow-up works also considered extending the hardness results of these two problems by obtaining either the same approximation factor or a different kind of penalty error. Thank you.
Do we have any questions from the audience? I didn't understand the concept. Very beginning of the talk, its structure cannot be used because there is some hardness reduction. The structure of Markov monkey orders, like the lattice in construct based on these orders, does it have like a structure you want?
So I said that, sorry. So we showed that there are special orders O for which their corresponding order LWE problems are equivalent with the unstructured LWE ones. So in this sense, the order LWE problems lose their algebraic structure. So they don't lead to efficient crypto primitives. I mean, even if they have ring multiplications in the orders, we cannot benefit from the multiplication of them because of this equivalence.
Okay. Okay, let's take the speaker. Our next speaker is she will talk about the improved analysis of the.
All right, so before I start, can you guys hear me without the microphone or should I have the microphone? Okay, thank you. Since that's been going in and out, it seems easier just for me to talk. Thank you for the introduction. So, like I said, I'm Ryan Carter. This is joint work with my brother, Max Carter, Hiroki Furo, and Daniel Smith-Tone. All right, so we're going to be talking about improved cryptanalysis of HFERP. Let me click right here. Okay. So we are going to be talking about 2 attacks on the multivariate crypto system HFERP. And so most of the talks today have been about lattice schemes. So a quick background on what a multivariate scheme is. This is going to be based on the MQ problem, which means that if you in general, it's difficult to solve a system of nonlinear equations over a finite field.
Sorry to interrupt. I think someone said it's better you said there for the recording.
For the recording. Perfect. Okay. So what we have is we will basically, when we have these multivariate schemes, we are going to be hiding a quadratic function that's easy for us to invert with these different compositions of linear maps on either side so that it looks like a random quadratic map, which is going to be on average hard to invert. All right, so let's start by talking about what the HFERP crypto system is. And in order to do that, we are going to be talking about all of these schemes that are going to go together to make up the HFERP scheme. So the first scheme is the hidden field equations, which is HFE. So this was introduced in '96 by Pataran. And what it is this is actually considered a big field scheme. What I mean by that is we're going to have a base field, which is FQ, and we will also have an extension field, which is FQ to the n. So we will start with some linear map U. Back over here. So we would take an input vector, it would be length n, we would mix it up by this linear map U. We would take that, use some vector space isomorphism, jump up to the extension field FQ to the n. And then we would plug that element into this polynomial that has degree bound D. And so the fact that this has a specific degree bound is what makes it reasonable for us to be able to invert if we know what the secret key is. Drop back down to the base field, and then we will mix everything up with another linear map T. This has now been broken. It was actually broken using min-rank attacks, which we will talk about later. There were then some different modifiers that were added to this, also broken. This is us breaking yet another version of this being added to modifiers. All right, so there's also the unbalanced oil and vinegar scheme. So originally, Pataran introduced the oil and vinegar scheme, which is going to be a scheme where we have these 2 different types of variables. That's why it's going to be called oil and vinegar, where you're going to mix them up, but they still kind of stay separate. So if you picture like an oil and vinegar salad dressing, you have it, you shake it up, and then you let it settle, they still separate. So there are these 2 different types of variables. So we can think about the first V of them being vinegar variables, and then the last O of them, or N minus V of them, being oil variables. So originally it was just called the oil and vinegar scheme because the number of oil variables and vinegar variables were the same. This can also be broken using rank attacks. And so this leads us to the unbalanced oil and vinegar scheme, where the number of vinegar variables is about 3 times as much as the number of oil variables. So there have been attacks on this scheme so that the sizes of the keys have had to grow, but this is an updated version of the unbalanced oil and vinegar scheme, which is normally just called UOV, is in the submission for the NIST additional call for digital signature schemes. So let's look at what the actual map looks like. So we are going to have a public key. This is going to be used as a signature scheme in general. Again, we are going to get the public key by this composition of maps where T and U are both linear, and then F is going to be something that is quadratic, where we can invert it if we know the secret key, but would be difficult in general. And this central map is going to be composed of v+1 different polynomials, where we're going to have this form. And if you first look at this, you're going to be like, okay, gross. Why is this anything where, like, what about this would be interesting if I have the secret key? So what I want you to notice is, and I don't know, hopefully you can see the colors changing. So the first double sum, so where we're having this quadratic term, that is a vinegar variable times a vinegar variable, because I'm only considering those indices. My second term is a vinegar variable times an oil variable. So what's happening is my oil variables are actually only occurring linearly. So if I know what my vinegar variables are, I can just plug in random values for those vinegar variables and then solve linearly for my oil variables. Because again, remember, this is a signature scheme. So if I'm just trying to find a specific preimage, so as long as the vinegar variables that I choose work, everything's fine. This was then can be extended to the rainbow signature scheme, which is when you take many different bands of a UOV central map, place them on top of each other, and then you get rainbow. We also have a plus modifier. And so this is where you have a public key, and then you just add, you plus some more random quadratic polynomials. So you would just choose them randomly, and then you append them to the end. And so once we take all of those different things that we just talked about, we're going to get HFERP. So this is a multivariate encryption scheme that is composed of an instance of HFE, a single layer rainbow map, and a plus modifier. And I'm sorry, this ran off at the end. So those are our authors, and it came out in 2018. I apologize that it scooted to the bottom. And so again, normally, so a few things we're actually going to consider. So it is technically like a rainbow map, but in general, the parameters are saying one layer of rainbow. So that is actually a UOV map, but HFERP sounded better than HFOO. So it is. So that's where the R comes in the rainbow, even though, again, we are actually in general talking about a single layer of UOV. And again, normally UOV and rainbow are a signature scheme. This is an encryption scheme because we're actually going to be getting the vinegar variables will be from the HFE map. So let's kind of look at how this is all going to go together. So let's look at the structure of this scheme. So we're going to have N variables and M equations. If you see this plus R is going to be kind of in gray. The reason for that is in the paper, it is considered to be 0. And in my thing that I'm about to show, when I put the R, it made the formatting not look as pretty. So the R is there, but you can kind of consider it or not consider it. So we have an input vector X. And again, we are going to start by mixing it up with some linear transformation U. So once we have X of U, or U of X, we are then going to take that value and plug it into 3 separate things. So first thing that we're going to do is we are going to consider an HFE central map. So I'm going to do this transformation where I'm projecting U of X onto just the first D coordinates. And then I'm going to apply that to an HFE central map. And I will get something in FQ to the D. I will also have a rainbow map, which is that thing that we talked about before, where we are linear in the oil terms. And then also I'm going to have some plus polynomials that are just going to be some random quadratic equations. We take all of this, concatenate them all together, apply the linear map T, which is going to take a linear combination of all of these different maps. And then we get FQ to the M. And so this is how we acquire the public key. And so I keep saying like, this is like, it looks very complicated. It looks like this could be cool. Like yeah, this should work. But this is what we're going to break. So just as a reminder, I kind of forgot to, I haven't been highlighting, this is what we're breaking. So, are there any questions about how the scheme is working before we go? Before we break it. All right. So let's start by talking just a little bit of background on the cryptanalysis techniques that we're going to use and just things we need to know. So something that is very effective against the multivariate crypto systems are min-rank attacks. So it's basically if you have some number of matrices, can you find a linear combination of them that have low rank? There are different algorithms that have different levels of complexity, but this is a very interesting and active field and also has implications towards other areas of research, especially things like code-based crypto. And so let's think about why a min-rank attack would be useful against the schemes that we are talking about. So let's first think about the HFE central maps. So remember, when I'm plugging something in to this, I'm projecting onto the like D coordinates. And so if I consider a matrix representation of the HFE polynomial, what it's going to look like is I'm going to have non-zero coordinates in the upper D by D block, and then everything else is going to be zero, because the first thing that I do is I project everything onto the first D coordinates. Let's think about what's going to happen with the UOV central maps. Well, remember, the only things that I have is I can have a vinegar times a vinegar, and then I can have a vinegar times an oil. So if I look at the matrix representation of one of these central maps, I can see that I'm going to have this zero n minus v by n minus v block, where that would be like an oil variable times an oil variable. So I know that all of those coordinates are going to be zero. So I know that I'm going to have the zeros in that lower coordinate. Plus polynomials, what's going to happen? We have nothing, no structure here. So it just is going to look, it's going to be random. All right, so we're taking kind of the idea that Ward Buelen's had this paper, Breaking Rainbow Takes a Weekend on a Laptop, and he was able to find a layer 2 oil vector Y by solving this system of equations, where we're looking for an element in the kernel of the public key equations. And then we also have this map that is also in the kernel, but of the discrete differential. So we have this thing where we have this linear system that we can solve, and then also have this thing where we're looking for a zero in the public key. We're going to take sort of a similar idea, but it's not going to be exactly the same. But what we can do is let's think about if I take all of my central maps and then I stack them on top of each other. So if each matrix was like a piece of paper, and then I put them right on top of each other, we can see that I have my HFE maps, my rainbow UOV maps, and then my plus polynomials. So this is what my central maps will look like if I think of them as a building. All right, so our first attack is a little bit similar to the simple attack, but we can also call this the divide and conquer attack. So the thing that we are doing is we are using this idea where I'm looking for a Y where two things are true. But now the two things that are true is I want to get this vector Z where I'm going to be looking at some pieces of information of the public key equations. So I want to find a Y that is in the kernel of some information of the public key equations, but also a Y that is a solution to the min-rank problem on my public key equations. So when I take a linear combination of my public key equations, I'm with this vector Y, I'm going to get something with low rank. Specifically, I want something with rank less than or equal to D. Why? Why would that be interesting? The reason for that is if I can find this this vector Y, then with high probability, it's going to be where if I take y times t, which is the linear combination of the central or of the outputs of f, then y times t inverse is going to have some length d, and then I'm going to have this 0 vector. Let's look at a picture because it makes it easier. Basically, this is what's going to happen, where when I take a linear combination of the central maps, if I think about that matrix on the left, I'm going to have something where I have coefficients up where my HFE maps are, and then everything else is 0. So if I do this linear combination, when I do the scalar multiplication and then I sum down, this is how I get this rank D solution. So the reason why that's interesting is with high probability, basically what this does is it gives us a way to get rid of that original U that we applied to the input elements X. Because we have found a linear combination that acts the same way as, or sorry, we haven't done that yet, but we're able to find this y that allows us to get rid of this u. So what we're going to do is we're going to use the basis vectors of this linear combination, and we're going to extend it to a basis, which is going to give us this block matrix structure, which looks like the HFE maps. So again, basically what we're doing is we are just able to say, hey, we've done something that allows us to have a way that looks like those original maps. So what we have is a linear combination of those maps. So we've basically found an equivalent U inverse. We have a way of getting rid of that first linear transformation. The next thing we can do is we can try to find an equivalent T. So remember, T is the thing that happens at the end. So if I have a way of getting past the U, how can I get a way to end up with the T, to get rid of the T? Well, what we see is that once we have that linear transformation, that new basis, I basically have a linear transformation of my public key equations. How can I solve this for a way that separates the 3 different layers of my maps? Well, what I can do is I can solve for zeros, different parts of zeros where I know that they'll be. So I know that for the first D central map equations, I'm going to have zeros. I'm going to have rank D, and I'm going to have zeros all the way over here. I know that for my ones in the middle, I'm going to have that lower right O by O submatrix that are 0, and then I don't have any specific structure on the plus polynomials. And so what we're able to do is we basically get a linear combination of the HFE maps, a linear combination of the HFE and the UOV maps, and then just a linear combination of all of them. So now I have these equivalent maps of all of the 3 different things. So that's our divide and conquer way. And then what we can do is we can just break each of the individual ones. We won't talk about this much, but something that's interesting that's an additional attack is instead of breaking up the system in this way where we say where are the HFE maps, where are the rainbow maps, where are the plus polynomials, we can just apply the big field support minors to HFERP in a way that was similar to the break of GEMS, which was HFEB minus. And the interesting thing is it makes it even more broken. But the complexity of this second attack, which I didn't obviously go into just because of time, the complexity of the second attack does depend on the degree bound of the HFE map, because what we're doing is we are basically going to just take the HFERP crypto system, find a solution to the min rank instance in the big field. Because remember in the HFE, we had that extension field. And so we'd be looking for an element with the rank that has the same rank as the HFE polynomial, that degree bound. So this is interesting. This one was even more effective against these parameters. But again, the complexity does depend on the degree bound. The other one doesn't. So with both of those together, it's really broken. The end. So thank you all for your attention. welcome to play around with the code. That's what's up on my GitHub.
Thank you for the talk. We have any questions from the audience?
So you have the array of gems, it could be a sort of D and a sort of B. So those gems are all of the HTTP base.
Yeah, so with the HFE break of the gems with the Petzold et al., there's a lot of HFE games that are just broken. I think that because of the interplay between you can't have the degree bound be too big or it becomes infeasible to use compared to if it's too small, then it appears that we can break it. It would be, you know, I don't want to be like, oh no, it's not worth looking into, but it does seem like they're very fun, but it does seem like most of the ways that we've been able to think of using them at this point have not worked. So it does seem like they are, it would have to be a very interesting way to be able to recover that sort of scheme to make it usable.
Yeah, so anything to do as to living text or prints everywhere.
I'm sorry, can you go the ABC? Yeah, I've heard of it. Yeah.
Yeah, so this is something I know it's only significant language, right? So you think
Can you repeat just the question part of it?
it's like do you think it's can be
Oh yeah, that I'd have to look into. I'm not sure. I'm not sure of my feelings on that. Yeah. Good question.
and
Yeah, that's the second Brian again.
Yeah.
Okay, this is the last talk of this session, and it's given by. She will be talking about fast and simple point operation. And equal point. I'm Ling Li, and this is a joint work with Wei Yu and Tong Xu. The scalar multiplication is the basic operation in elliptic curve cryptography, which is widely used in reality. There are three main methods to accelerate the scalar multiplications. The first one is improving the point operations. The second one is using the efficient endomorphisms. And the final one is reducing the Hamming weight of the scalar. And this work, we improving the scalar multiplication by the first method, that's improving the point operations. As we can see, in this work, we focus on the fact in curves like perform ADD1448 and ED448. The Edwards 448 and ED 448 are two elliptic curves that are specified by the list. And the Edwards 448 is allowed to be used in the EDDSA, which is the Edwards curve digital signature algorithm. The story of the Edwards curves goes back to the Euler stack. And in 2007, Edwards generalized the curve that Euler and Gauss studied to the form, and it is soon introduced in elliptical curve cryptography by Bernstein et al. The research on the Edwards curves developed rapidly in 2007 and 2008. Here we list the work that studied the point operations on different Edwards curve forms. And the M here means the finite field multiplications. The S here means the finite field subsuperiors. And the D here means the finite field multiplications with constant. That means that the addition algorithm is complete when A is a square and D is a non-square. If the parameters A and D does not satisfy the condition we mentioned, they are no longer complete. So ever since the Edwards curves introduced in the elliptic curve cryptography, the scalar multiplications on the Edwards curve has become the leader in the multiscalar multiplication. There are two works in this paper that have caught our attentions. First, when A equals -1, we have a very efficient addition formula. And second, Kohel provide the form in the P3, which shows that A and the parameter A and the parameter D shows very good symmetry. So the good probability that A equals -1 holds that should hold for the D equals -1. In addition, we have that the parameters in the Edwards 448 and the ED 448 are shown in here, and we can see that the parameters A equals 1, not the -1. It is because that -1 is not a square when in this field, but we can transform D to be -1 by the isomorphism. Actually, Kohel showed that there are 4 addition formulas on the twisted Edwards curves. And Hazel et al. Studied the formula 1 and 4 detailedly. In this work, we studied the formulas 2 and 3. And the formula 3 is complete when D is a square and A is not square. Handling the prime order subgroup is very easy since there is a lemma provided by Sedlex et al. That they show that the exceptional cases would not happen in the prime order subgroups. So we can straightforwardly derive the addition formulas and unified addition formulas and doubling and tripling formulas, disregarding the exceptional cases. Here we list the unified addition formula that derived for the formula 3 as an example. We additionally obtained 8M and 4D algorithm by cleaning covector techniques. which use more multiplications with much smaller constant to replace the multiplication with a large constant. And if we employ 4 professors to compute point addition, all these unified addition formula cost 2m and 1d, and the uniform addition formula that with the clinical denominators computed much smaller d. Except the case of the prime order subgroup, we also studied the case of subgroups with the order 2q and 4q by the following 3 reasons. The first, we are hard to check whether a point is a point that in the prime order subgroup, but in ED 448 and Edwards 448, it must be a point in the 4q order subgroups. Second, we want to preventing the attacks that exploiting the small cofactors. And the third reason is that we want to combine it with the decaf strategy, which is a well-known strategy for the advanced curves. So we restudy the now the above lemma that we have mentioned that proposed in the previous works is invalid, is not enough here. And so we reanalyze the exemplifications by the following lemma. And the R1 here is a point in the 4 order subgroups. As we can see, the exceptional cases is occurred around the P and the R1. And they all of them can be represented with P and -1's addition, or the minus P and R1's addition. And also we analyze the exceptional cases for our first addition formula. So by the analysis, by our lemma, we have found that the unified addition formula is also complete for the 2q order subgroup. And the exceptional of cases of the single scalar multiplication can be handled by limiting the range of the scalars. However, the exceptional cases of the multiscalar multiplications cannot be solved by handling the scalar, since the relationship between the input points are blending. We observe the following facts. The first factor is that the actually external cases that would make the computation errors are only 2 cases. And all of these 2 cases link to an equation that y1, y2 add a plus x1, x2 equals 0 by the lemma. Thus, we can distinguish whether our unified addition formula rests correctly by checking this equation. Secondly, both of the elements in this equation are computed in our unified addition formula and computed in the Hissels et al.'s unified addition formula. The A not equals -1 version, which costs a little bit more slower, a little bit more multiplications that with 9m and 2d. But since A is still a square and D is a non-square, so Hissels et al.'s unified addition formula is complete in this way. So we can combine our unified addition formula with Hissels et al.'s results. And we have derived algorithm 1, which is complete for the multiscalar multiplication. When M1 at D1 not equals 0, it runs for our unified addition formula. And when they are equals 0, it turns to the hits out at all cases. Since that the -1 at D1 rarely occurs to be 0, so it's in most of the time it runs in our unified addition formula. So this is all the things about our works. Thank you for the listening and attention. So